Chapter 7 is entitled Special Purpose Semiconductors. There are many different special purpose semiconductors. We will cover some of the more common. They are the silicon-controlled rectifiers, the diac, the triac, and the field effect transistor. Let's examine the first of these, the silicon-controlled rectifier, which is commonly referred to as an SCR. However, before we get to new material, let's briefly review some of the semiconductor devices we have covered previously. In earlier programs, we have covered the single p-in junction and saw that this could be used as a diode or rectifier. Then we progressed to the transistors, which had two p-in junctions. The transistor could either be a p-in-p transistor or an n-p-n transistor, depending on how the layers of p-type material and n-type material were arranged. Now we'll look at some semiconductor devices that have 4 layers, 2 layers of p-type material and 2 layers of n-type material. This 4-layer arrangement gives us 3 p-in junctions. There are numerous special semiconductor devices in this p-n family, but the most common one is the SCR. The SCR is used in control circuits to control the amount of current or voltage applied to a load. It is called a silicon-controlled rectifier because it is a rectifier which is controlled and is made from silicon material. As we just discussed, the 2-layer rectifier had 1 p-in junction and 2 leads. The SCR differs from the simple rectifier in that a 3rd lead is connected to one of the layers which will act to control the flow of current through the device. This 3rd lead is called the gate. The gate is connected to one of the layers of p-type material like this. The 3 leads are called the anode, the cathode, and the gate. This is the symbol for the SCR. It is a diode symbol with the line representing the gate added. The gate line may be shown slanting in from either side. You will recall that when we connected the plus terminal of a battery to the p-type material, which is the anode, and the negative terminal of the battery to the n-type material, which is the cathode, the p-in junction would be forward biased and would conduct. If we connect the plus terminal of the battery to the outermost layer of p-type material in the SCR and the negative terminal of the battery to the outermost layer of n-type material, the SCR will not conduct and no current will flow. In order for the SCR to conduct, it is not sufficient to have a positive or plus voltage on the anode and a negative or minus voltage on the cathode. A positive voltage must also be applied to the gate for current to flow through the SCR. When sufficient gate current flows, the SCR will turn on suddenly, much like a switch that is suddenly closed. In this respect, the SCR resembles a transistor. In a transistor, the base current controlled the amount of current flowing through the transistor. However, once the SCR is conducting, or in other words, current flows through it, the gate cannot control the amount of current which flows, nor can the gate turn off the SCR. Thus, the gate of an SCR is not equivalent to the base of a transistor. We can now see that the SCR is not like a rectifier or a transistor, but is an entirely different device used for different purposes. We now have the SCR turned on, or conducting. How can we turn it off, or stop it from conducting? Removing the positive gate voltage, or even applying a negative voltage to the gate terminal, will not turn it off. There are 2 ways we can turn off the device. One is to remove the voltage from the anode. The other is to place a short circuit from the anode to the cathode for a very short time. Either method will stop current from flowing through the SCR, and both methods are used. However, it is more common to turn the SCR off by removing the anode voltage. Let's look at the characteristic curve of the SCR to see what makes it different from an ordinary diode or rectifier. The curve of an ordinary diode looks like this. Remember that the diode did not conduct, or current did not flow, until the p-in junction became forward biased, and then the current increased like this. Now let's look at the characteristic curve of the SCR. It resembles the diode curve, except there is a portion of the curve that juts out. It is this characteristic that keeps the SCR turned off until gate voltage is applied. When the gate voltage is applied, then the SCR turns on and begins to conduct, and the curve will now look like this. After it is turned on, the SCR has characteristics similar to an ordinary diode, and removing the gate voltage will not affect the current flowing through the SCR. Now let's look at a circuit using the SCR as a control device. If we apply a positive voltage to terminal 1 and a negative voltage to terminal 2, the SCR will not conduct since the gate voltage is 0. Now let's close the switch. A positive voltage will be applied to the gate and the SCR will conduct. RL is the load. R1 is used to limit the gate current, and the diode is in the circuit to prevent gate current from flowing in the opposite direction if the polarity of the voltage on the input were reversed. If we apply an alternating current, or AC, to the input terminals 1 and 2, the SCR will act as a half-wave rectifier. It will conduct during the positive half cycle, but it will not conduct during the negative half cycle. Remember, we said that once the SCR was turned on, it would conduct until the anode voltage was removed. Well, when we apply an AC signal, the anode voltage is positive for 1/2 of the cycle, then it goes through 0 and becomes negative for 1/2 cycle. When the signal goes to 0, the anode voltage becomes 0, and thus is effectively removed. During the negative half cycle, the SCR is reverse biased and will not conduct. Thus, if we apply a 60 Hertz AC signal, the anode voltage will become 0 and be removed 60 times each second. The output of our SCR circuit will look like this. The SCR conducts during the positive half cycle. We will indicate it is conducting by shading the curve during the conducting part of the cycle. Let's modify the circuit by replacing the switch with a variable resistor R2. The amount of voltage applied to the gate can be regulated by the variable resistor R2, and this will determine when the gate will turn on the SCR. The variable resistor can be adjusted to let the SCR turn on anywhere in the positive half cycle between 0 and the maximum voltage. The output voltage across RL will look like this. The SCR will be conducting only during the shaded part of the cycle. If the load RL were replaced by an electric motor, the circuit could be used to control the speed of the motor by varying the time the voltage is applied to the motor. This is the principle used in variable speed electric drills. The trigger is connected to the variable resistor so that the position of the trigger determines the voltage applied to the motor. SCRs are used for motor controls for both small and large motors. Other uses include relay controls, time delay circuits, regulated power supplies, heater controls, phase controls, and other uses. The external appearance of the SCR is similar to a transistor. Since most applications require controlling large currents, most SCRs resemble power transistors, and adequate heat sink must be provided. Now let's turn our attention to the diac. The letters in the word diac may have originally stood for diodes and AC current, but if so, that distinction has been lost with usage. Today, diac and triac are pronounced as words, and the letters don't really stand for anything. The diac is a 5-layer device. It has 2 terminals and somewhat resembles 2 Zener diodes in parallel. The characteristic curve of the diac shows that it will conduct when either positive voltage or negative voltage of sufficient magnitude is applied. This is the symbol for the diac. Since the diac can conduct in either direction, it can be used in AC circuits and is often used in conjunction with the triac. Like the diac, the triac is a 5-layer device, but a gate is added to control the turn-on conditions. The triac is also somewhat like the SCR in this respect, but it differs from the SCR in that it can be turned on in both the positive and negative half cycles. The characteristic curve of the triac looks like this, and as you can see, this portion resembles the SCR curve here and an inverted SCR curve here. This is the for the triac. Let's look at a control circuit using a diac and a triac. This circuit controls the voltage applied to the load RL by switching the triac on and off during both the positive and negative half cycle. The shaded portion of the cycle indicates conduction. The amount of time the triac is conducting is controlled by R1. The capacitor, C, allows the AC to flow, but prevents the rectified DC from flowing. We can replace the load resistor, RL, with a light bulb and have a light control circuit, or as it is more often called, a dimmer circuit. The position of the variable resistor will determine how much voltage is applied to the bulb, and hence how bright it is. We have seen how semiconductor devices can be used to control circuits. In many applications, a resistor could be used to control the voltage applied to a motor or light bulb, but all the current flowing through the motor or bulb would have to flow through the resistor all the time. Since power is determined by the current squared times the resistance, a lot of power would be wasted as heat in the resistor. In the SCR and triac circuits, current flows only during part of the cycle. Therefore, the current is turned off during the rest of the cycle, and power is not wasted. The final semiconductor device we will look at today is the field effect transistor, or FET. The field effect transistor differs from the regular transistor, or junction transistor, in that it is a voltage control device rather than a current control device. It may consist of a bar of N-type material with P-type material embedded in a band around it. This is called an N-channel device, and this is the symbol for an N-channel FET. It may consist of a bar of P-type material with N-type material embedded around it, in which case it is called a P-channel device. And this is the symbol for a P-channel FET. The 3 terminals are called the source, gate, and drain. These correspond to the emitter, base, and collector of a regular junction transistor. The amount of current flowing from the drain to the source is controlled by a voltage applied to the gate. Since the field effect transistor is a voltage control device, no gate current will flow. This is in contrast to a junction transistor where base current always flows when it is conducting. This is a typical small signal amplifier circuit using an in-channel field effect transistor. Amplifiers using field effect transistors have extremely high input resistance, often several million ohms. Because of this high input resistance, they are often used in electronic meters and instruments. Field effect transistors are also low noise devices, which makes them useful in stereo and hi-fi applications and in medical electronic circuits. This concludes Chapter 7. It is also the conclusion of teletrain's basic course on solid-state electronics. In this 7-chapter course, we have endeavored to give you a background upon which to build an understanding of solid-state electronics. I'm Dave Brown for teletrain.